Thank you, thank you. So, yes, exactly. I always try to ask nice questions, so if you have questions, there is Kavita inciting the crowd. All right, so I sent an abstract about distributionally robust optimization with martingale constraints, and but I am not going to talk about that. I could talk about that, and I can answer questions, but I think I thought it was probably better to sort of to have some continuity with the lectures and sort of take from where I left off. So exactly where I stopped and then sort of continue, because this is an area of research that I think is fairly statistical. I am super excited about this. It combines a lot of optimization, operations research, data-driven modeling, and also model misspecification. And I think it's a very, very versatile framework that can be used to produce a statistical inference in infinite dimensional spaces, potentially in graphs, and so I think it's very, very rich. And so I think I would like to share that. Okay, so this is from a paper that is called Robust Wassestein Profile Inference. This is a joint work with Karthik Murthy and Yen Kang. And this is a paper that you can find in the website of Advances in Applied Probability. Okay. So the motivation, I'm going to sort of resume from where I left off in my talk. So the motivation, this is really an inference technique, but the motivation really comes from distributionally robust optimization. So as a motivation, remember, we're interested in solving this following class of problems. So we have a formulation in which the optimizer or the model is going to pick a decision. The decision is going to be robust to adversarial perturbations in Wassestein space. Okay, and we prove that this, as a particular case of this formulation. Yes, great. So Pn. Pn could be whatever, but I'm going to be assuming in this talk that Pn is the empirical measure. Sorry? He has a parameter theta. No. This. So let me explain. Right. So a particular case, you should keep in mind, for example, the case in which you have a loss function, which is L of z equal to z squared, and you have a model, which is a linear regression model. You have data of this form, and you want to estimate, you want to solve for minimizing over beta, maximizing over the Wassestein distance between P and Pn, less or equal to delta, and the Wassestein distance here that I'm going to be using is so I'm gonna write here rho. So this is the I'm going to use mu and v here. So this PV is mu and PW is nu. So this is a minimization over all probability measures. The distance between V and U, use LQ distance to the power rho, so that's the rho order Wassestein distance, and this is what we're going to be using here. For example, in this case, if I put equal to 2 here, and I write expected value under P of Y minus beta transpose X square, and I take 1/2 here, I guess this is the same as minimizing over beta expected value of Pn, 1/2 Y minus beta transpose X plus square root of delta norm of beta P. Okay? If I select the cost function assigning infinite cost of transporting Y, so just transporting X, remember we recover this type of estimator, right? And so this was one particular case. So applying it to linear regression, you recover a square root lasso regularization by Belloni, 2011. If you instead are interested, for example, in estimating a logistic regression model, so in the context of logistic regression, you get a completely analog estimator. In that context, you will have to put rho equal to 1. And in this case, what you need to put here a square here. Okay, so I'm gonna better write it like that, rho, so it gets like this. It's a little cleaner. And in the context of logistic regression, so I'm gonna write that model. So example 2. So if you want to minimize over beta maximum over Wassestein distance Pn less or equal to delta expected value under P of the loss in the logistic regression case is the likelihood. So that's minus Y times beta transpose X. You obtain that this in this. Write a bit bigger. Yes, I can write a bit bigger. So this is going to be minimized over beta expected value Pn plus delta norm of beta P. Okay, so in these examples, 1 over P plus 1 over Q is equal to 1. So you always have, in these examples at least, you obtain the dual norm. In the lectures, I explained why that happens. And so this and many other examples motivate this. Okay? So in the lectures, I finish exactly like this. I finish explaining why this, you have this duality. We worked out why do you have these representations in these examples. And I said in the last lecture, how do you pick delta? So my goal in this lecture, so the goal is to explain, so work out the statistical theory for optimal choice of delta. Okay? All right, so the way in which I'm going to choose delta, I'm going to remind you. What I'm going to do is I'm going to define a set of parameters. So these are the set of thetas. Now I'm going to go back to the general case. So I'm going to go, these were motivations. This is choices for different specifications of loss functions and different parameters. So theta corresponds to beta in these examples, but I'm going to emphasize that this is a much more general theory, so I'm going to use this specification. I'm going to be assuming that loss is convex in theta, but I'm going to explain to you what really is required for the statistical theory. Okay, so that is a convenient thing, but it's not necessary. I'm going to explain. So this is going to be the set of thetas that depend on model P, such that theta of P is the arc mean of this optimization problem. Yes. And what I want is this generates a confidence region, so you can interpret this to be as a confidence region. So the intuition is that every model here, if you have chosen delta correctly, every model is a reasonable variation of the data. And so for every such model, you can pick a decision. And the idea is that we don't want to have the right model. The idea is we want to make the right decision. So we have this set of decisions. What we want to do is, this is increasing set as a function of delta, and what we want to minimize delta subject to the probability that the correct decision is in the set delta Pn, which is the confidence region. That's at least 1 minus alpha. And this is user defined. So that, for example, could be 0.95. Okay? So this such that such that dp Pn is less or equal to delta. So you speak over the models P that are less than delta. Yes?
That set contains all kinds of decisions, right? Not just the correct.
This set contains a lot of decisions. Yes. But all of these decisions that it's contained in the set, those are decisions that corresponding to a model that you told me was a reasonable variation of the data. So this stuff contains what you are assuming in your formulation is reasonable. Okay? So now this problem looks complicated. So instead, we are going to reformulate this representation. So the event, I'm going to rewrite the event theta star is a lambda delta Pn. This is going to be the same as the event that function that I'm going to define, which I defined it in the lectures, but I'm going to redefine here. Theta star is in this set if and only if Rn theta star is less or equal to delta. And I'm going to define what is this Rn theta star. So Rn theta star is going to be the distance between Pn and the set of probability models that make theta star optimal. So that's the distance between is the distance between Pn and the set of P such that theta star is okay. So what's let's just this equivalence? It looks a little confusing or complicated, but it's very simple if you think about it in words. Like just in words, what does it mean that Rn theta star is less or equal to delta? Rn theta star is equal to delta if and only if there is a P in this set of probabilities that is within delta distance and for which theta star is optimal for that P. Where that would mean that theta star has to be in this set because this is the set of P's that are within delta of Pn and that make they correspond to optimal decisions, right? So if there is a theta star here, then there is one P that makes that optimal and is within delta. Well, therefore, the distance to that has to be less than delta because there is one there, right? So then the whole point is to understand what happens here, okay? So now the question is simply what does it mean to theta star? So what I want is I'm going to rewrite this under convexity assumption. This is minimum dp Pn such that expected value of the gradient with respect to theta, hx theta star is equal to 0. Okay? So now I'm going to stop here and tell you what is really the point here. And so I start here motivating the definition of this function and the statistics from the DRO, Distributionally Robust Optimization formulation. But in reality, really you can define the distance between your sample or some benchmark model that you have, right, to a manifold of probability distributions that can be defined according, for example, to linear constraints. And those linear constraints, you can define, well, they integrate certain expectations. If here this is an infinite dimensional set, and you have many, many constraints, and these linear constraints determine the distribution, then you recover the Wassestein distance. Because that will be the distance between the distribution that integrates the expectations explicitly, that's P star to Pn. So this thing recovers the Wassestein distance. And you can make that set of constraints smaller and smaller, right? If it's finite dimensional constraints, then this is the case that I'm having. You can have lots of constraints, and you can inform in this estimation problem what do you care about. So you want to test an hypothesis for a variable, for a theta star, for a parameter, and as long as that parameter complies with these expectations, then you are fine. Then you say, my model is good for that, right? So you don't have to now approximate the true distribution, because what we know is that dp star to Pn, so if Pn converges to P star, so you have IID data, right? We know that, that this typically is going to be at least n to the power minus 1 over d. Okay, so under assumptions, even in the case of uniform distributions, right? Dudley, this is a very classical result. With high probability, you at least need these many samples to estimate the distance. So this approach basically relaxes the Wassestein distance, allows you to do inference depending on what you really want from the distribution, not the whole thing. Okay? So that's why I think is a very powerful approach. So I'm going to introduce a notation. I'm going to let h of x equal to gradient of theta, h of x theta star. I'm not going to be carrying this theta star all the time. And what I'm interested in is in estimating what are the asymptotics of this object. So what I want, goal, or objective, to show that n to the power rho, or that Rn of theta star approximates some 1 over n to the power gamma. We are going to identify what gamma is, times z, and we are going to identify which distribution is. So this is where the goal, right? So we want to understand what's the law of Rn of theta star as n goes to infinity, right? And this law is not going to scale. There is a scaling here, and we're going to identify the scaling, and whether it's this random variable, we want to identify that. Also, what I want, this is goal number 1. Goal number 2, I want to identify the geometry of this set. So what is this set? So if I take this lambda delta Pn, for example, and I subtract beta star, so that's a confidence interval, so it's going to contain beta star with high probability. What I want is once I identify the delta n, the optimal delta n, which is given, the optimal delta n is going to be delta n star is going to be equal to z 1 minus alpha, so this is the 1 minus alpha quantile of z, and then I divide by n to the power gamma. Once I identified gamma, what gamma is, I plug in the optimal delta. I'm going to plug it in here. I guess this set is centered around 0. I'm going to blow this up according to some scaling, which we know has to be a square root of n, right? And then I want to get converges to some set, right?
Theta star, right?
Sorry? Theta star, sorry. Okay, so I want to see what's the shape of this set, how does it depend on Q, etc.
What convergence are you using there?
That's convergence in the Feld topology. Yes. All right. So I'm going to state the theorem. So theorem under regularity. So we're going to see, I am going to go back and tell you what is the regularity. I'm going to leave this space blank. Since I'm going to sketch the proof, I'm not going to do the proof in whole detail, but I'm going to do it with enough detail so that you can see where the assumptions are used. On the regularity assumptions, if the cost function, the transportation cost function is norm of x minus y, q here, and you put rho here. And what you are saying is that the Wassestein distance to the power rho here, rho Pn, the formulation I'm imposing is the Wassestein distance to power rho is less than delta. Okay, so that's in the DRO formulation. Okay, so I have this. This is chosen, then n to the power rho divided by halves by 2, r n theta star converges weakly to phi star of z, where, or I'm going to write here w, where phi of z is equal to rho minus 1 expected value of the norm of gradient of h of x. I'm going to use q here, and to the power rho divided by rho minus 1. Okay, so this is what I want to do, and W is a normal with mean zero and variance sigma, where sigma is the covariance of hx. Okay, so this is what we want to. This one we want to. What I want to show you. Phi star is the Fengel conjugate. So phi star of z is equal to the supremum over lambda. Yeah. Okay. Okay, so the first step is to write the dual. So minimize dppn such that expected value under p of h of x is equal to 0. Yes? Sorry, yeah?
What cap h? Is it just h of x?
So remember I introduced, oh, sorry, small h, yes. Small h, yes. Yes, I changed, yeah, now this is the gradient, yes. So h of x, because I don't want to keep erring. Yeah. Okay, so this is an LP, right? So we can write this LP, this is, so this is minimizing over all pi's, the integral of norm of x prime minus x q to the power rho pi dx prime, and you have the constraint that the integral over x and x prime of h, I'm going to use here prime. So just to emphasize, x prime goes with the probability measure p, x's will go to the probability measure pn. Okay, so I'm going to use that convention, so x prime pi. And then what is the other constraint? I have the integral over x prime of pi dx prime, that's equal to pn dx. Okay, so this is formally the LP. Right, so I'm minimizing overall couplings between x and x prime, such that x prime has distribution, Well, that's free, so it goes wherever, right? That's because that's the thing that I want to minimize. Yes, equal to 0. All right, so that's a dual problem in a standard form, right? So this, you have equality constraints everywhere, pi greater or equal to 0. Sorry, that's an LP in a standard form. The dual problem is maximize the dual variable, so it's lambda times 0 is 0, and so this is alpha Pn dx, so that's alpha Pn subject to the constraint that lambda h, this is capital H, lambda hx prime, lambda hx prime plus alpha x less or equal to norm of x minus x prime q to the power rho. And so that's the same as, so alpha wants to be as large as possible, but it has this bound for every x and x prime. Alpha is the dual variable that goes with this constraint. So this constraint has attached to it an alpha x, and this has attached to it a lambda. Okay, so it's this lambda transpose here, right? And so this is the same as maximizing, and alpha of x is less than this, so that's the maximizing expected value under Pn. And then this is the infimum over x prime of norm of x minus x prime q to the power rho minus lambda transpose h x prime. Okay? All right, so at this point, this is really the rest of the to guess this result. Really, the thing is just to use intuition, because it looks a little intimidating, but all what you need to do is to intuit what has to happen. So everything is anchored according to the displacement. So displacement, this is the optimal transport measure here, right? So what we want is to pick something that in the end is going to be close, is going to be close, have the same statistical fluctuations as the empirical mean, as empirical measure. So empirical measure, we know that the statistical fluctuations are governed at a high level by a central limit theorem. So what I'm going to do is I'm going to postulate a local central central limit theorem locally. So I'm going to postulate that x and x prime are going to be order 1 over root n away. That's going to be my guess. I'm going to say that's going to happen even locally. And once I impose that, everything is going to fall into place. So I'm going to have this lambda. So since that is the key, I'm going to introduce this delta. I'm going to write here delta q to the power rho minus lambda transpose. I'm going to have x plus delta here. Okay? And if delta is really close to, if delta is really of order 1 over root n, I better start subtracting h of x, because then h of x is going to be really close to h of x delta. So I'm going to get max over lambda expected value of Pn. I'm gonna pull this outside. I'm gonna subtract here an h of x delta, so I'm gonna have to add negative lambda transpose EPN hx, and then I'm gonna have here plus the inf, and I'm going to already start thinking about the representation I want, which is this soup. So I'm gonna write this as negative expected value of Pn of the sup of lambda transpose h x plus delta minus h of x minus delta q to the power rho. Okay, so now I'm ready to do what I say. So I'm going to start saying I'm going to introduce delta bar equal to delta divided by root n. So I'm going to get this delta here minus 1 over n to the power rho divided by 2. Okay, so you see now I'm producing it already here. So this is going to be delta bar divided by root n. Okay, now I'm going to multiply by root n and divide by root n here. So this is going to converge to the derivative. Then here, under the null hypothesis, I know that EPN hx times root n converges to a normal with mean 0 and covariance sigma, which is the covariance of hx. So I'm going to multiply here by root n and divide by root n. And now I'm going to introduce another scaling, which is lambda equal to lambda bar. And I need to put whatever I'm missing for this, right? So that's 1 over n to the power rho divided by 2 minus 1 divided by 2. And that gives me max lambda bar minus lambda bar EPN. I'm going to actually use h bar n here. So this is h bar n. And this is minus expected value under Pn and sup of lambda bar and this part here. I'm going to write gradient of h of x times delta minus norm of delta rho q. And I already have introduced here an approximation, which is little o of 1, right here.
Should also be extracting out the fact that
yes, I'm going to put it here. Okay, so now you see what's going on, right? So that's here. There is a little o of 1 here, and this is the assumptions go here. So what I need then, I need continuous differentiability. Continuous differentiability, no, not really convexity. I don't need convexity. Here, all what I need is that the null hypothesis is valid, that this holds. So I could be testing a stationary point of the optimization problem, but I do need continuous differentiability. Something that when I start working with this max, I don't want this guy to pick something that makes this 0. So I need to avoid the degeneracies here of the covariance. So I need to avoid the degeneracies. Covariance, and what I want is some control on growth. So in particular, this function turns out gradient of h of x. Any norm that you want here has to be constant norm of x to the power rho minus 1. This has to do with proving the lower bound, not for the upper bound. For the upper bound is very, very mild. And upper bounds are, because in the upper bound, in the upper bound case, what happens is at this point you can ignore this little o of 1, solve for delta, right? So at this point here you can supremize, and here what you get is this is norm by the Helder inequality. This is norm Q, norm P here times norm Q, right? So you see the norm P here popping up, and this should have been norm P. Sorry about that. And so now this just becomes a one-dimensional optimization problem that you can solve, and you would obtain as the solution precisely this part here. This is Z. So once you solve this one-dimensional optimization problem in delta Q, then you obtain that part, and you see this string of inequalities, you have n to the row divided by 2, This was just Rn. So we started here from Rn, and we obtained Rn equal to 1 over n rho to the power 2 times something that is stable. Okay? So in the paper is like 46, 48 pages long, and the part of the reason is that long is because there is a supremum here, so you need to compactify. But now the compactification is easy. You can see from here that if you basically need to localize the delta bar, and you need to localize the lambda, and then that takes some work. Okay. But the intuition of why you get that type of result is basically this. Okay, so now what I want, let's see, I have here, yeah, so so one thing that you can do is in the linear regression case, I'm gonna make a comment here. So here, if you solve this optimization problem, right, you get delta bar Q times delta by Q star. So you solve this optimization problem and you ignore this part. So you get delta bar Q to the power rho minus 1 times rho. That's equal to the norm of lambda bar transpose h of x, gradient. So this is a matrix now. This is really the derivative of h. Remember, h was a list of equations, so the derivative, this was going to have a Hessian. So that's this becomes a vector now. And so that's equal to the power p. So you can solve for delta star. Okay, so here's some remarks. Remark. If your loss function, if this really h of x was now would be h of x and y, right? Was y minus beta transpose x times x. So this is the linear regression case. In the linear regression case, this quantity as a function of x is quadratic. So this step here, when I linearize and apply this Taylor expansion here, that will be exact. So in that case, there is nothing, there is no big O or whatever. You could actually carry on like infinite sample, all of this infinite sample. And what you would obtain is that Rn of theta star is less or equal to the norm of zeta Zn Q square divided by the variance of the error in your linear regression model under Pn, the variance of the error. Okay, so this is what you obtain if you just massage this, because in this case, everything is rho is equal to 2, you have squares, there is no approximation, it's exact in this case here. And you can obtain an upper bound like this, where Zn is equal to 1 over root n times the sum of xi times the errors ai. So in this case, you can analyze what are the quantiles here as the dimension grows under the standard assumptions that are in the literature of high dimensional statistics, and you obtain the right scaling. You obtain the quantiles of this random variable under the standard assumptions that you have normalized xi's, that the sum of x squares is equal to 1, for example. You will recover the prescription of high dimensional statistics because you have this finite sample bound. So that's one remark. So this is a much more general theory for sort of choosing delta as n goes to infinity, but when you specialize it to the case of linear regression, you can analyze this object that these EIs are the errors in the linear regression. So if the errors are IID, Gaussian, you don't even need sub-Gaussian tails. I mean, you can just simply, if the maxima grows not like log of D or the square root of log of D, but something different, just plug it in, okay? So it recovers that. So one thing I just want to point out, the case of rho equal to 1, this is something that is very interesting because it's interesting for the logistic regression. If you look at this expression here, when rho is equal to 1, this quantity is going to blow up unless this random variable is less or equal to 1. So if this norm is larger than 1, with positive probability, this one here, then as rho goes to 1, this is going to blow up to infinity. But this guy here is, this appears basically right here. So this player, which is the outer player and wants to maximize, is not going to allow this guy to blow up to infinity. That will be minus infinity. So therefore, in that case, you can guess, and that's correct. So for the case rho equal 1, if you have density, what happens is that you have 1/2 Rn theta star, and this converges to the maximum over lambda in some set C, and this is W transpose lambda. And this set C is the set of lambdas such that the probability that this vector is greater than 1 is 0. So you need to remove those, that's the lambda set. So that becomes complicated to use in practice, but the rest you can use in practice because you can use plug-in estimators to estimate this expectation. Okay, so now I'm going to show you some pictures. I'm going to show you some pictures of the set gamma. Sorry?
Going from pi to pi star also to do.
What is from theta to theta star? Where?
No, you have to find actually find
the phi star, yes. So this, what I'm going to show you, there is another paper that's about confidence regions. So what we show is that an empirical version of this thing also converges on the set of which is the confidence region. So you can just plug in the confidence, the empirical, and then you can get the same result. So it's asymptotically equivalent. So for when rho is larger than 1, you use the obvious plug-in estimators and you are perfectly fine. So every statistic that you see in the right-hand side, you just plug in the plug-in estimator of this C, use your favorite consistent estimator for theta star, your empirical version of this, and you go on, right? And also, that paper provides the support function of this convex function. And that's important because the support function is the one that actually draws the confidence region. So in the paper it's explained. So that support function is used to produce the pictures I'm going to show you. So I mean, while this lowers, I think this machinery, this robust profile function, this R of n function, can be used, for example, while this thing lowers, can be used to test, for example, if random variables are in convex order. So how do you design a test if x and y are in convex order, for example? So what you would do is you would look at the empirical data, and you look at the manifold of distributions that are consistent with convex order. By Strassen's theorem, that tells you that this happens if and only if they form a martingale. You look at the minimum distance between P and Pn, such that this is equal to this. You compute the statistics, the score statistics for this. And you reject the null hypothesis if this quantity, which you can estimate from data in practice, because this is an LP, if this is greater or equal than the statistic. So you will reject the hypothesis. You don't have, you can test the hypothesis of fairly complicated quantities because you have this geometry of the Wassestein distance, like very high dimensional and the objects that are, I mean, this was an example of testing, for example, if you have convex order, you can do other things. I mean, the properties, as long as the properties are defined in terms of some linear manifold, then you can just do this. Okay, so the picture, so it turns out that this function, the limiting function, once you center, the scaling we have guessed, this gamma turns out to be, this is for the case rho equal to 2, so that corresponds to rho divided by 2, which is 2 divided by 2, which is 1, so that would be gamma equal 1. So this is what I'm illustrating here. And the function is the level sets of that convex function. That's phi star. C is a matrix since everything is centered around beta star, so we need to multiply by the covariance to make a change of coordinates, but that's not crucial. Just think of C as identity. Sorry, I'm going to almost done. So here are some pictures of what's the geometry of that set. So this is for the linear regression case, and of course I'm doing for dimension 2, because I cannot do, well, I mean, I could do other things, but it will look less clear. So you see the controls are really smooth, very nice, because even though these shapes, these convex shapes, which are the level sets of this phi star function, might be complicated to compute, with this support function that we compute in the paper, it actually becomes really fast to compute this, like on the order of, few seconds. So this is the case when I pick, this is the transporter P, that's Q equal to infinity, that's P equal 1, P equal to 1.5, so Q is the dual vector. What I'm showing here is the ring, red ring is the distributionally robust optimization estimator. The cross here is the true value, and the center of the ball is the empirical risk minimization estimator. So this shows the different geometries. These are 95% confidence balls. This is the case. This is the P equal 1, so Q equal to 1. And you see these like different shapes that are informed by the geometry. So I think an important open problem that we're kind of trying to work, all of these are sharp confidence regions, by the way. All of these are 95% confidence regions. It's not like upper bound or whatever, like it's just different shapes of confidence regions. When you choose a confidence region in statistics for a multidimensional statistics, well, you might choose an ellipsoid because sort of makes sense, but it's not as obvious as in one dimension. In one dimension is an interval, and but in multiple dimensions you might choose, there are many things that you could do, right? So choosing what's the best confidence region is also a question of, well, what do you want or what do you like? Right? Distributionally robust optimization, this formulation allows you to implicitly select an optimal one, the one that is implied by your transportation cost function. So that one generates an optimal one, and this is the ones that I'm showing here, right? So
asymptotic intervals, or exactly?
No, this everything is as n goes to infinity. Like it's the central limit theorem here in these guys, right? So these are just funny sort of convex functions, but are in a way like informed by the distributionally robust optimization formulation. So if you want to create the distribution, the game, the min-max game, to protect against something, and you inform the transporter, what is it that you care? He should go and explore, try to damage you in that, with those attributes, right? So these are, I worry that I'm going to be unprotected here, go and do a smart job. He's going to optimize and going to try to do the best it can. Once you inform him that, then he's gonna go back to you and tell you, well, my best guess of what the decision is you should take this confidence region. You shouldn't take that one, for example, or that other one, because then you will be choosing betas that are harmful for you. And you told me you care about these things. So I'm telling you what's the best one, according to what you told me. So that's, I think there is a lot of, it's a different way of thinking about the statistics, I think, thinking about what you don't know. I think this has potential for like ill-posed problems, It's a different way. So that's something I didn't have time to talk about, but this is the DRO one. This is the distribution and robust optimization. So that one is always there. It's not obvious though, because I didn't say that, but it turns out it's fine, it's there. That's it.